For decades, we have treated lead poisoning like a closed chapter in public health, associating it almost exclusively with the era of leaded gasoline and mid-century industrial regulations. But because the metal is non-biodegradable, the millions of tons mined and processed over the last century never vanished. It remains embedded in our environment, persisting in soil, plumbing infrastructure, and the walls of older homes. Over the last few decades, medical consensus has shifted as researchers identified health risks at lower and lower concentrations. This led the Centers for Disease Control to repeatedly lower the threshold for clinical intervention. Public awareness often focuses on acute, high-dose poisoning events. The far more common reality is continuous, low-level exposure that accumulates quietly over years. Lead persistence represents an active, microscopic assault on human biology, currently accumulating undetected within modern populations. Clinical data now shows there is no genuinely safe level of lead. Even trace amounts in the blood, concentrations under 5 micrograms per deciliter, trigger systemic physiological breakdown. At these low levels, the metal interferes with the peripheral autonomic nervous system and promotes vasoconstriction, which drives up blood pressure and significantly increases cardiovascular risk. It also suppresses the innate immune system by impairing macrophage function and shifting antibody production toward allergic responses. In children, these trace amounts delay skeletal maturation and dental development. The brain is the most sensitive organ. Early life exposure correlates with measurable drops in IQ, loss of brain volume, and an increase in neurobehavioral disorders. These failures aren't caused by brute force, but by a precise chemical deception at the cellular level. When entering the bloodstream, lead relies on a specific chemical disguise. As a divalent cation, its structure and charge perfectly mimic essential minerals, primarily calcium. Our cells are lined with transport proteins designed to bring calcium inside. These mechanisms mistake the imposter metal for a nutrient, pulling it into the cell. This mimicry allows the toxin to bypass biological security checkpoints, substituting for calcium to cross the blood-brain barrier. Once inside the brain tissue, it concentrates heavily in the hippocampus, a region critical for learning and memory. The body's calcium infrastructure becomes the exact network lead exploits to access our internal systems. Inside the central nervous system, lead targets NMDA receptors, the ion channels responsible for fast neurotransmission. By physically binding to these receptors, lead blocks actual calcium from entering the synapse. This halts the calcium-dependent processes required to form new memories and establish learned behaviors. Beyond synaptic disruption, lead accumulation in the cells generates high volumes of reactive oxygen species, throwing the body into severe oxidative stress. Usually, antioxidant enzymes clear these free radicals, but lead binds directly to these enzymes, effectively neutralizing our natural cellular defenses. Without those cellular defenses, oxidative stress shreds red blood cells, leading to hemolytic anemia and inflaming the kidney tubules. Lead disarms the cellular mechanisms meant to fight it, leaving our internal organs defenseless against widespread physiological chaos. Clinical studies reveal a strange pattern. 2 individuals living in the same environment with identical exposures often show radically different health outcomes and lead levels. The variable is the patient's DNA. Variations known as single nucleotide polymorphisms, or SNPs, multiply biological vulnerability. Specific SNPs in the ALAD and VDR genes alter encoded proteins. These variants produce enzymes that permanently trap positively charged lead ions, unlike baseline proteins. This genetic shift changes exposure kinetics. Individuals with these variants retain lead in their blood and soft tissues longer, drastically increasing the cumulative damage. Genetic variance determines whether an individual's physiology efficiently processes the toxin out or acts as a biological magnet that holds onto it. Because the body processes lead exactly like calcium, it deposits the heavy metal into our bones. In adults, 80 to 85% of all absorbed lead is stored directly in the human skeleton. The deep cortical bone acts as a latent toxic reservoir, locking the metal away from sensitive soft tissues, often for decades. However, this storage is not permanent. During periods of high bone turnover, such as pregnancy, lactation, or menopause, bone tissue is reabsorbed, leaching that stored lead back into the bloodstream. Understanding this life cycle gives medicine new ways to respond. Researchers now use early biomarkers, like the kidney injury molecule KIM-1, to detect cellular damage caused by lead long before systemic failure sets in. Medicine can also utilize targeted nutritional strategies. By flooding the body with adequate levels of actual calcium and vitamin D, we can physically outcompete the imposter molecule, blocking its cellular uptake. Identifying the specific genetic vulnerabilities and pathways lead exploits allows researchers to develop targeted strategies to counter the metal's silent, enduring legacy.